Hey everybody, I don't know if you could tell, but that was just a killer moonwalk you just missed right there. It was awesome. I don't know if you can see the feet and everything, but it was perfect. How you guys doing? This is probably the last video I'll do, and should be back live with you next class to teach you the rest of the course. Today what we're going to do is learn about the chain rule, which is another differentiation technique. And so far, we've kind of transitioned from doing the limit definition for all the derivatives to looking at shortcut rules. But as you're finding, the shortcut rules, although it started pretty easy at first with the power rule and differentiating polynomials and stuff like that, the product rule is a little harder, and the quotient rule is a little harder yet. And we'll be getting into situations where they're still going to be difficult, but still a lot easier than it would be to do all these problems with the limit definition. Okay. So today we're going to look at composition functions, which is functions within other functions, and learn how to differentiate those. And then we'll just continue kicking it up a notch every time we get back together. Okay. So today's the chain rule, notes for section 3.6. So let's get started. Now, last time we learned about the derivative of trig functions. So for example, we learned that the derivative of the sine x function is cosine x. So the next step that I'd like you guys to think about is, what if you wanted to find the derivative of something like sine of 2x? How would you find the derivative of sine 2x? Or, let's say you wanted to find the derivative of the sine of x squared. Wonder what those would be. Well, probably, unless you've learned the chain rule before somehow, you probably think, well, there's not much difference between these two problems. The derivative of sine of something is going to be cosine of whatever that something is. So you probably think that it's just cosine 2x. Here, you probably think, well, this is just cosine x squared. Okay. And turns out that's wrong. Totally wrong. Not even close. Well, actually, it is a little bit close. But that doesn't work. So just like I did with the product rule and the quotient rule, I want to first convince you that that doesn't work with a simple example. Then I'll show you the technique that we use to differentiate composition functions like these. They're called composition functions because there's functions within other functions. Okay, so let's consider this simple example. This is a composition function. There's this function inside, which is the 2x squared minus 3, and the outside function is the squared function. Okay? And again, I'm considering a very simple situation here so that I can illustrate why that method that I just talked about doesn't work. And I could do it a different way. Okay? I'm actually going to do a couple of different examples like that. So you might think, again, to find the derivative of this, that this is just like the function x squared. So to find the derivative of x squared, it would just be 2x. So you might think, well, I'm just going to take the 2 down in front of this stuff and lower the power by 1. Okay. And if you do that, that gives us the answer, if you distribute the 2, of 4x squared minus 6. And again, the question is that right? Well, again, we've got a different way to do this problem. If I go back to the original, I can actually square that out using this algebra. So I have to FOIL this times itself, and the answer that I would get would be 4x to the 4th minus 12x squared plus 9. Okay, so this is the answer you would get if you took this times itself. Now, the reason I'm doing that here is that I know how to take the derivative of that. That's just a polynomial. So the correct answer would be derivative of this term, 16x cubed. Derivative of this term, 24x. So I know that is the right answer. Which means this last result was wrong. It's not quite that simple. Okay? All right, so let's do another example. And I know probably I've made my point that that doesn't work, but there's still something I want to accomplish from this. Okay, so another example like that. Let's say if I take the function y equals 3x to the fifth to the fourth. Okay, again, it's a composition function inside of another function. Now again, what you might think about is treat this as something to the fourth, x to the fourth. The way you differentiate x to the fourth is you take 4 times it by this, lower the power by 1. Okay? It's almost common sense to think that that would be the thing. So if that's what you're thinking, you know, that's not a bad thought. We just have to make sure that it works. Okay? So what I would do to simplify this then is to actually cube this part. So if I cube the 3, I get 81. If I cube the x to the fifth, I get x to the 15th. And then 4 times 81 is going to be, let's see. Do something wrong here. Oh, I know, 3 cubed is 27. See, I need you guys here. When you're not here, I make mistakes, and I got no one that telling me I make mistakes. Okay, so that's 27 because 3 cubed is 27. Duh. So now 4 times 27 is 108. X to the 15. Okay, so again, the question is that right? Well, this is another problem that I could do in a different way. So going back, I can write y in a different form because I could actually fourth power that. 3 to the fourth power, that one is 81. X to the power, multiply the exponents, I get 20. So that's just a different form of the same function. But that I know how to differentiate with the power. So 20 times 81 is 1,620. Lower the power by 1 is 19. So again, I know that's right. Which, comparing that to this, clearly that's not the right answer. This is wrong. Now, in addition to convincing you that that doesn't just work, I also want to use these two examples to figure out, well, how do you do it? What is the easy way to differentiate a composition function without simplifying it the way we did? So I want you to look at the results in each of these two cases. What I want you to think about is, what you would have to do to the wrong answer to get to the right answer? Because it's actually close. And in fact, I'll manipulate your thoughts a little bit. What would you have to multiply this function by to get this answer? Think about it. What would you have to multiply 4x squared by to get 16x cubed? Well, 4x. Notice if I multiply 4x times 6, I get 24x. So it's actually not too far off. I'd have to multiply by 4x. So if I take that wrong answer that I had, multiply it by 4x, distributing it, of course, I would get this. Okay, now look at the other example. How would I get from this wrong answer to that right answer? What would you multiply by? Well, it's just a monomial this time. So 108 times it by what is 1620? You just use your calculator to do a division. And 1620 divided by 108 turns out to be, let's see, I think that's 15. Okay. And then what do I multiply x to the 15th by to get x to the 19th? Well, that's x to the 4th. So I can take the wrong answer, multiply it by 15x to the 4th to get the right answer. Okay. Now the question is, how would you figure out this if we didn't already know the right answer? How would you have figured out that multiplication term? In back to the last example, how would you have figured out this 4x term? Okay. Well, look at the original problem. Where can